So welcome, good afternoon. I'm Chris Wilson. I'm a developer advocate on the Google Chrome team. And one of my personal passions, and part of my job, of course, is web audio and the web audio API and some related stuff that I'm going to talk about today. So I wanted to get into this, and I actually, how many of you might have seen the video of the presentation I gave last I/O on web audio? I see like 2 hands, 3 hands. Okay, well, you don't count, Peter, sorry. Great, so if you haven't seen that, there's a ton of technical detail in there, a bunch of like, this is exactly how you do some of the things that I'm going to talk about. I'm actually not going to go, for the most part, into quite as much depth, although I am going to dive into the code in a couple of places. That one was really broad. It took me an hour, and I actually nailed it with like 13 seconds left. And I don't want to move that fast because I want to cover more in this deck. But there's a web audio talk out there. You can watch it if you want more detail on a bunch of this. It's actually decent, which is, my bar for saying my talks are decent is pretty high. So, but I wanted to get my clicker to work. I wanted to start off by talking about why we need another audio API. We already have this great HTML5 audio tag. It's not even that old. Like, it's only been out for a few years. And it kind of works really well. Like, it's far better than object tags, and it's way, way better than using BG sound, for those of you who remember that. But audio kind of wraps everything about, the audio tag, I should say, wraps everything about audio up into one step. It wraps up loading, decoding, and getting ready to play. You can actually tell it not to automatically play into this one element. And this one element is kind of the controller of all the audio behind that. And sometimes this is totally what you want to do. There are 2 things that this is really good for. One of them is just playing an audio file whenever you want to, whenever it's ready, I mean. And the other thing, and if you don't want any precise control, and the other thing is it's really good because it handles streaming for you. So you don't have to go implement a streaming, adaptive streaming system to get content as it comes in. If you want to do those things, just use the audio element. So none of this is audio element is bad or anything like that. They actually complement each other pretty well, which I'll talk about a little bit later. Now, the web audio element, the web audio API, on the other hand, provides 3 main things. The first one is really precise timing of a lot of overlapping sounds. So one of the struggles with the audio element was developers started trying to build games using the audio element. And it turns out this is not a really good way to build audio for a lot of games. This may be really loud, so we'll turn it down. And I think the first big game customer using the web audio API was Angry Birds. Eek. Knew it was going to be loud sooner or later. And you know, for anybody who's familiar with Angry Birds, which of course is basically everyone at this point, wow, I must not have played on this machine before. You know, it has a lot of sound elements going on at the same time. Like, you get a lot of rocks bouncing and stuff like that. And this is kind of challenging to do with the audio element because you need one audio element for each one of these aural elements happening. And many systems actually start topping out. They start being very resource constrained when you have even just 5 or 6 audio elements at the same time that are trying to play. They start competing for resources. So one of the things that the web audio API is very good at is doing very precise timing, lots of sounds together. I'll talk about scale in a couple of places. The second thing is web audio provides a pipeline for audio. You can do routing, you can have sends and returns and things like that if you want to build your system that way. You also get built-in effects and filters that are managed for you. So if you want to do delay effects, if you want to do filtering, to do low-pass filters or things like that, those are built in. You don't have to go write FFT code or find an FFT library and hand apply that to the stream of audio data. In fact, the great thing about web audio is all of the processing of that actually happens on a separate thread. You basically set it all up, and then it manages the process of processing all that audio for you. So you don't have to worry about it on your main UI thread. And if you have some bit of JavaScript that takes 100 milliseconds to run, it actually doesn't glitch your audio because your audio is happening on a separate thread. And then finally, the Web Audio API provides hooks to analyze and kind of visualize audio data on the fly. I talked about how we have filters built in. We also have an analyzer built in. And this is a very, very old demo. This is one of the first Web Audio API demos I think we did, which hopefully it will, for some reason not, there we go. And this is basically just kind of a graphic EQ spectrum analyzer, so you can see what's going on in the spectrum space. Building this, if you actually go, this is an example from HTML5 Rocks. And if you go and look at this, the source code for this, it's actually an amazingly small amount of code. There is more code in the loop that draws all of these lines than there is in the web audio part of it, which is kind of amazing for what it's doing. So I took this, since there aren't very many of you who were around for my I/O talk last year, I took this and I immediately started playing with it, and I wondered just how far I could get this to go. So I built a vocoder, and I'm going to guess not very many people understand what a vocoder is. It's the robotic voice effect you frequently hear, the whole Styx domo arigato thing. That's a vocoder, heavily used in a lot of electronic music and a lot of music from the 80s. But it's actually this process of taking an input file or an input stream and chopping it up into frequency bands and then kind of tracking each frequency band and applying those spectrum characteristics over time to a different signal, usually an analog synth or something rich in spectrum analysis. And I ended up with a demo that looked about like this. So it takes this file of just me talking.
407 years ago, our fathers brought forth on this continent.
And it maps the frequency characteristics over time and applies them onto this really nasty sounding signal. Trust me, I know it sounds awful, but when you put them together, you get a robotic voice effect. Right? And you can see the frequency bands bouncing here because I animated it just so you could tell what was going on. Now, the really interesting thing about this to me is I realized after a while, this is actually very complex. This is setting up hundreds of nodes and connecting them all together. There's a lot of filters. This is a 28-band vocoder, which is a pretty big vocoder in terms of like comparing to an analog vocoder system. And the only bit of my code that runs while this process is going is the stuff that shows you the visual displays. Like my code is not sitting there moving internal sliders on sounds or anything. In fact, after I did this demo for I/O last year, we added live input support to Chrome's web audio implementation. And it took me about 20 minutes to get it running in the vocoder. And now there's this little thing that says live input, and you can click it. And I would love to click it, and the only problem is it feeds back really, really nastily if you're not using headphones. So I'm not actually going to click the button. But all of this stuff is online already. You can go play with it yourself and test it out. Oh, forgot a part. The other cool thing about this is because you've just set all of this up and it's running this web audio code in the background, you can change things about the web audio setup as it's going. So if I tell it to start playing this, I can very easily do things like change the synthesizer voice in the background and change the pitch, or change the noise levels or things like that. And all that I'm doing is changing properties in the web audio setup. It's set up this huge graph of nodes and plugged them together. So that's great, but you're thinking, okay, I'm not actually going to build a vocoder. The uses of a vocoder are pretty limited, to be honest. There's some great music from the 80s that uses it, but other than that, not so much. But there are some really important uses of this kind of audio, even simplistic scenarios of this API. The first and foremost one, of course, is gaming. Like, I'm actually kind of a weird person to be really interested in audio because on any given day, I can guarantee you that the audio is turned off on my iPad and my tablet and my laptop, just because I'm in meetings all the time and I don't want stuff to start playing or anything. But at the same time, having audio feedback to your applications just as part of the user experience is actually really powerful. It's the same thing as lighting up a button when someone hovers over it so they know it's clickable, or lighting it up so that they know they've actually clicked it. You can also give that kind of feedback through audio, and it's pretty easy to do using this API. The part, of course, that I'm really excited by is music applications and audio processing, moving all of this music industry production stuff into the web platform, and we can now start doing that because of this API. So if all you want to do is build kind of feedback, like beeps kind of thing, noises that go on when when your character jumps in a game or something like that, it's really pretty basic. You use XML HTTP requests to load up a sound file. You use web audio to decode this into a flat buffer. And we have decoding API built in. And then you create a source node, you point it at that buffer and say, start playing. And then that's pretty much it. It just starts playing. And it will take care of cleaning up after itself as well, like any of the transient memory that it's using. If you release that, it'll play all the way to the end, and then those just get garbage collected when they're available. In fact, I/O last year, I was hard at work. It was 2 weeks before I/O, I think, and I was hard at work finishing up my talk. And one of my colleagues, Colt McCandless, who was working on this game, because he was doing a gaming talk, like how to build games in HTML5, he was building this grits game. And let's see if this actually loads because I'm on Wi-Fi. And this is an open source game. It's an example of how to build games in HTML5. And he came to me and was like 2 weeks before and said, hey, we kind of need some sound effects in here. And I've got something partly running, but do you have a sound manager I can just drop in? Because I know I'm supposed to use web audio now. I'm like, well, let's take a look. Let's sit down and talk about it. Because he'd never looked at web audio at all. And in about 20 minutes, he got the idea that actually he didn't really need the sound manager that he had before at all, because he didn't have to sit there and manage, well, I have to keep 6 audio elements open and I have to switch it back and forth between which sound files are playing. And when I want to play a file, I have to see which one's available. Like, you don't need to do that because the web audio API is designed to be this very lightweight API. So he can do things like, he's got a background track going. You can hover over things and it makes these neat little sounds. And the game itself has tons of sound in it, although the server I noticed this morning was down, so I'm not going to attempt to play it. So if this is what you want to do, just load and play sounds, you basically load the sound and get a buffer. And that's what this first function is. It's just dead standard XML HTTP request call. All that it does differently than some calls is it asks for an array buffer back so it can get it binary data. And then it calls decode audio data. So if it's an MP3 file or an OGG file or any other data type, encoding type we support, it'll automatically decode it, get it as a buffer. And then whenever you want to, you can call play sound. Once you've decoded it, you can just play this buffer by creating a buffer source, pointing it at that buffer, and connecting it and starting it. Once you do that, you can actually, you'll notice, this actually throws away the reference to source node. Like, once you've hit play sound, start is not a blocking call. It just falls on through. And you've released the source node. So once it's done playing, all of that object goes away. The connection to the destination goes away. You don't have to worry about hanging on to this or managing it at all. And the first time I saw this, I thought this was really wasteful. Like, you're creating, it's kind of like you're creating a whole audio tag, inserting it into the document, and then forgetting about it, and the next time you want to play the same beep noise, you create another one. But that's not really how the web audio API works. The buffer is the big chunk of memory, and you can reuse that as many times as you want, including simultaneously. It's also kind of important to understand that connect call is setting up connections within a graph. And when I first started playing with the web audio API, I had a tough time visualizing this, so I actually built this tool that I also demoed at I/O last year, and I've tweaked it a little bit since then but I have some more ideas of what I want to do to it. I just haven't gotten to it. But it's a great way to kind of explore the API, because what it does is it lets you create a buffer source node, and I can just connect to this, which is hard to do on my trackpad, but come on. And once it's connected, if I hit play, equivalent to hitting start, you can hear the noise beeping. But I can also do things like create one of those spectrum analyzers. And of course, I have code built into this that's actually visually displaying it. That's not part of the API, but it is pretty straightforward. And you can see how that comes out in the analyzer. And I can also do things like adding filtering on it. Like, let's change this to a drum sound. Come on. I had to make the connection points really big so that I can actually hit them when I'm up on stage. And let's loop this. And interestingly, that doesn't seem to be going through there. So the gain in this filter type shouldn't matter, actually. There we go. Now you can hear the filter in there. So all of this, again, all I'm doing is setting up a node, creating these connections between the different nodes, and then twiddling parameters on the node. All of the processing of the audio is happening on this separate thread. I don't need to directly even understand the math that's going on there. And I also don't need to worry about the visuals of this display interfering with that audio and making it glitch. So this playground is kind of a good way to explore how graphs can work. I keep meaning to have it output what the web audio code looks like too, although I haven't quite gotten to that part yet. So part of the reason that we do this glitching, or one of the ways that we do this preventing glitching, is most of the time you're not actually directly affecting the audio. What you're doing is you're scheduling an event in the future. So you're doing something like, instead of saying, I want to play this sound file right now, you say, I want to play this sound file precisely at this point in the future. And the scheduling in web audio is so precise that you can actually stack cycles of a waveform next to each other if you want to. And it will actually play them as a continuous wave. It won't like have skips or anything in the middle. So you can do things like this, where this code is set up so that it will actually do exactly the same thing as that play sound code did, except it will do it once every second in the future. So the last call there, start, actually says context.now plus I. Context.now is the audio context current time, and I'm adding multiple seconds to it. This is a loop from 0 to 9. So I'm adding 0 to 9 seconds to that. And basically, I call this, it schedules 10 copies of this sound playing in the future. And then they just kind of happen because they've been scheduled for me. I don't have to sit there and try to call it again. This is really critically important because, as most of you who have ever played with set timeout know, you don't actually have very high precision with set timeout. Set timeout can be really, really out of order, really not when it's supposed to get called back. If you have things like garbage collection happening, even in the best of times, you're probably not going to get below 3 or 4 milliseconds of latency on set timeout calls. And they get throttled really badly when your tab is not active, when it's not on the front. They actually get throttled down to a second on most browsers. So this way, the web audio API can just handle all of the things being scheduled in the background. Now, I actually wrote a longer article about this. I'm not going to go deeply into the details of this. There's an article on HTML5 Rocks about how to do kind of dynamic scheduling. Because the problem with scheduling like this code, is once you've called start 10 times to schedule these things in the future, you can't do anything with them. You can't actually cancel them and get rid of them, or you can't say, oh wait, I didn't want it to be a second in the future, I wanted it to be 1.1 seconds in the future. You don't have that control anymore because you've already scheduled them. In that case, you need to do this kind of partnership between the scheduling and using set timeout. That's pretty much what this article is all about. But it means you can build things like a full-on drum machine. And this is actually also a pretty old demo. This one's been around for a while. But it basically just lets you set up beats. And if we want, we can completely reset this, start it playing, and we'll just and then you can tell I can do things like change the pitches of things live, because although it's scheduled those sounds in the future, it's not scheduled like 20 copies of them into the future. It's only scheduled a couple, 10 milliseconds, 50 milliseconds ahead of where it needs to be. And I can change things that are past that. So I can change the tempo or whatever, and it takes effect fairly quickly enough so you don't really notice, but they're very precisely placed other than that, so you don't notice any glitching in the rhythm or anything. If you try to do a drum machine rhythm using set timeout, you'll actually usually hear that it's not quite right, like it's not regular, because our brains actually hear that reasonably well. It's one of the reasons why drum machines felt so mechanical for a while, is because they were extremely precise, and a human drummer, even a good human drummer, usually doesn't have exact precision in where they're placing all those hits. Oops, that's not what I meant to do. Okay. Now, the other interesting thing about scheduling in web audio is it's not actually just scheduling starts and stops. It's not saying, hey, I want to start this sound file now and end it now. That's not the only thing you can do. You can schedule any parameter, and you can schedule fades of any parameter. You have this API called audio param, and almost anything you would think of as an input value to the system, so gain, volume on a gain node, or delay time, or things like this, they're all actually audio params. And in addition to the value being exposed on that audio param, you actually also have, you can set the value at a particular time in the future. You can tell it to ramp from that value to another one. You can tell it to do exponential or linear ramps. You can tell it to do successive approximation, all kinds of things. And then the system does this for you. So if you want a really smooth crossfade, all you have to do is set this up as an audio param fade and forget about it. It will just magically do its business for you. And it does this at the audio rate precision. Like it's actually smoothly doing this inside processing blocks even in the audio system. So like this example here basically just fades in a sound and then fades it back out. Or fades in a gain node, I should say. Whatever you've connected to it, it will fade that in and then fade it back out. So it fades it in, starts by setting it to 0, and then at 2 seconds in the future, it's setting it to 1, so full gain. And then 2 seconds further in the future, it's setting it back down to 0. So it fades it in over 2 seconds and then fades it out. So pretty easy to set up. Now I talked about effects earlier, but I didn't actually go into the details of what kinds of effects are in there. And this is the place where if you want more detail about what and how these things work, like what convolution does or wave shaping, go look at my I/O talk. It has a bunch more detail in it. Filtering in general is one of the basic musical tools, which is super helpful. We also have things like positioning and panning and Doppler effects even. So you can do 3D positioning if you're building a 3D shooter game or whatever. It's very easy to set that up as a 3D sound space and just kind of share it directly with your graphics code. Now, obviously, advanced game audio, 3D games or things like that, you will need these things for. You may not need them in Angry Birds, but there is actually a lot of demand for many of these features. In fact, if you look at this, Filtering can be used to do environmental effects. So you walk in and you're like partly behind a wall from somebody and they sound muffled. You can do that. You can get radio effects or telephone filtering, so it sounds like you're talking over a telephone or something like that. Compression is usually used to keep from getting distortion on loud noises, and all kinds of things. Convolution is reverb, basically, so you can get sort of real space simulation. Now, I did say at the very beginning that the audio tag and web audio complement each other. This is also true because web audio can process the output of an audio element. And this seems a little weird if you just want to play back a sound file, but you have to keep in mind that audio elements also do streaming. So an audio element can handle adaptive streaming for you, but then you can pump it through a processor to do compression or to do filtering or analysis or any of these other kinds of tools. I keep wanting actually to go hack into Google Plus Hangouts because we use them on our team pretty heavily, and I work in a different office than most of the team, so I'm on video conferences all the time, and you're always in a set of a bunch of different people, and there's the people in the conference room who are really, really quiet. And then there's one guy with a really, really hot headset mic that's really, really loud. And I was in one the other week where I had to sit there with my hand on the volume control for an hour-long teleconference and like pull it down and then push it back up because I couldn't hear one guy. And the other guy was actually causing people to knock on the conference room door and say, "Could you turn it down?" And also this applies to WebRTC streams as well. So once we move Hangouts to WebRTC, I should be able to do that. Now, musical applications, kind of the same set of things. Like you need filtering, compression, that sort of thing. You really start wanting audio input even more. Delays, you start needing to be able to synthesize audio, so doing oscillators, being able to draw sine waves and sawtooth waves and that sort of thing. Set up envelopes, which I kind of already showed you how to do with audio param scheduling. You probably want to do offline processing too for things like convolution effects that are pretty expensive in CPU time. And this is also a place where I made this point in my I.O. talk as well, but I think that it kind of got lost. If you look at most complex effects, like if you're trying to replicate what a guitar chorus pedal does, this actually is a lot more complex than just a single filter or a single delay node. It's actually a delay that's getting changed by a low-frequency oscillator. Well, you can actually model that inside the Web Audio API, set up a low-frequency oscillator, and then anything that's an audio param you can route a signal into, which is basically what I did in my other set of examples, other set of demos, which you also really need headphones for, because otherwise it feeds back really, really badly. So go take a look at the deck later with a headset on and play with it. Just like regular, iPod headphones actually work reasonably well for these kinds of things. Because we now have input as well. And this was the huge thing for me over the summer was when we got input turned on and started to turn it on. It's actually, it's mostly done now, but it's still behind a flag, so you have to go in and enable it in flags. But now you can do audio recording. So see how well this picks up my voice, but this is a test. And you can see, what that looks like. You can even grab it, and I have this little encoder that's just encoding it as a WAV file. This is a test. Not too bad. And you can also do different effects. You can use this to drive games. Some people have actually started building games that use audio input as a way to control things. In fact, I think the Cirque du Soleil Chrome experiment that was done late last year, used audio input in one spot. And you can also do things like instrument tuning. And this is a quick and dirty demo that I wrote. And if you're interested in pitch detection or tuning, don't look at this code because it's awful. This is not the way you should do pitch detection at all. It's really, really super naive. I just wanted to see if you could do it. but you actually can, and we'll see how bad my whistling is here. So you can tell it actually picks things up, but it gets a little bit confused. Whoops. And it's on GitHub. And of course, you can use this, like you saw with the recording example, to do analysis of audio signals as well. And I do want to say, by the way, I'm very careful to use the term input, not microphone, because they're not actually the same thing. And people think of this as, oh, this is just for recording things off the microphone that's built into my laptop. Well, the microphone that's built into my laptop, despite it being a nice laptop, is kind of crappy. I mean, I have much better microphones at home. And I also have instruments that I can directly plug into my sound cards. So I have a guitar sitting in my office now because I can plug it straight into the audio inputs, play around with chorusing and distortion effects and all kinds of things. And I can build my entire amp modeler, if I want, in the Web Audio API. And there are actually some really great open source projects right now to do exactly that and to sort of build plug-in effects pedal modules. Pedalboard.js is one of the best ones. Now, I also looked at this late last year, I guess, and said, okay, well, I've built all these other things. I've always thought it should be super easy to build a synthesizer using Web Audio. So I went and did that, and so for those, how many people in here are like synth fans, played around? Wow, okay, awesome, that's a lot. So this is kind of based on the voice architecture of a Moog Prodigy synth, but it is not intended to be a replication of a Moog Prodigy. So don't file issues saying, why doesn't this sound right? Or why did you use a different LFO signal or something? But I built this thing, and it took me about a week, beginning to end, to build this entire synthesizer. And it turns out it took me 85% of that time was building the UI. 10% of the time was tweaking the end ranges of each one of the parameters, like figuring out, oh wait, attack should really go from 0.0001 seconds to 2 seconds rather than 1 second to 15 or whatever, because that's not musically useful. And only about 5% of the time remaining was what it took to write the core code that does voice architecture, that sets up a synth sound and everything. The rest of it was all hooking it up. But you can also play around with all the parameters, because this does actually fully work now. There were a few parts that I found a bunch of bugs in our code actually discovering this. But if you want to get your really low maybe not that low. There we go. So all these parameters are directly controllable in here. And one of the really cool things about this was if you actually go back and look at the source code to this, the voice architecture part is pretty simple. The UI part was really, really hard. And one of the things that I wanted to do, and I'm working on getting back to, is taking the same thing and plugging in different synthesis architecture. So doing a simple playback, sample playback synth and things like that. So I decided to take this guy and create a template. So this is basically the same piece of code, like forked this off of GitHub, but ripped out all of the UI and ripped out basically all the voice architecture as well, and just stuck in a simple sine wave with an envelope on it. And if you look at the source code for this, whoops, not that one. If you look at the source code for this, this is it for creating the voice and starting to play it. So in this, when I get a note in, I create a new voice object, and the voice object says, okay, I have a note number, translate that into a frequency, and then create an oscillator, which defaults to sine wave, set its frequency, create a gain node to be my envelope, and then it just sets up an attack time and a linear ramp for the attack time, and then a exponential decay to the sustain level, and then call start. And that's it. Like, I just wrote a synth voice right there. And it's kind of interesting because I used to be I started out in my teens as a really big synthesizer fan. And I always thought it was kind of weird because at the same time I was really getting into computers, I always thought it was kind of weird that they called the people who design voices for synthesizers, they call them synth programmers. Like, that's their job title, basically, is synth programmer. And I thought this was a little weird because they're just sitting there twiddling knobs, right? They're not actually doing any programming. But it turns out this blurs that line pretty heavily because you can add new features to your synthesizer very easily by going in and tweaking the Web Audio API code. If you wanted to add, a couple more oscillators or some other weird, make it a 4-stage envelope or a 15-stage envelope or whatever, on the synthesizer I had, all you have to do is go add a little bit more code into it. Okay, so now I want to jump to my new favorite topic, which is how you control all of this. Because for those of you who didn't see me set up here, I actually have a little keyboard right here that I'm using to play most of this. That synth code actually does support mouse clicks on the keys. It supports the computer keyboard actually gets turned into kind of a virtual music keyboard. It actually does touch support as well if you're on a touch device. I'll talk about that a little bit later. But I really wanted it to be controlled by a real device. In fact, this is how I got interested in the Web Audio API to begin with. Was I had an iPad, and with iOS 4.2, Apple added core MIDI support. Like, if you have the camera connector kit, which has a USB plug on it, you can take this keyboard, plug it straight into here, and use it to control the software synthesizers. And by the way, there's like 400 different software synthesizers or sequencers or things like that up on the App Store right now, because I counted, interestingly enough. And I think I have most of them on here, actually. But I looked at this, and before that, it was like I had these really great software synthesizers, but they were toys, because I wasn't really going to go play music by tapping on this touchscreen. I mean, there were some interesting other applications, but there wasn't this, I have a synthesizer that I'm really going to play. Well, it turns out now, for the last year or more, if you go into your local music store, go into your local Guitar Center, go into Best Buy even, actually, they have a great music section now. They sell keyboards exactly like this one, except they have an iPad slot on the top. And this is totally what I would suggest to anyone who wants to get into synthesizers today, just because you can swap out the software very easily, and it is just a controller. And my goal really was to say, okay, now let's take the iPad out of the equation. Why isn't that just any web platform device you have sitting around? Why isn't that my laptop or my iPad or another tablet or whatever? So there's a standard called MIDI, and I meant to bring one of the actual original cables, but I didn't. It used to be this weird round 5-pin DIN connector, runs at a really slow and very odd rate, 31.25 kilobits. Most of the time, though, no one uses that anymore. For the last 10, 15 years, most MIDI devices, certainly not all of them, most of them are actually what's called USB MIDI. It's a class of USB device. So the two MIDI devices I have sitting up here are both USB, like they both have a USB plug, but they're automatically recognized by my laptop as a USB MIDI device. They don't have a different device driver. They don't have to be specially recognized or anything like that. Now, unfortunately, a lot of the time when I say MIDI, people think of this in the 90s, there was really cheesy background music on web pages. A lot of that was standard MIDI files. This is totally different. When I say MIDI, I'm really talking about this idea of taking musical controllers and plugging them in and getting that as input into the web platform and being able to send messages back out to synthesizers or lighting systems or all these other kinds of things. So I actually am the co-editor of a standard for this called the Web MIDI API to add MIDI support to the web platform. There is not an implementation of this natively in any browser, Chrome included. There is, however, I wrote a polyfill for a probable web standard that is based on an NP API plugin So basically, you include this JavaScript file into your project, and it looks just like Web MIDI is implemented as long as the user has this plugin installed. So you have to get people to install the plugin. But other than that, it works really well, and it feels just like the real thing for the most part. If you are at all interested in getting MIDI added to the web platform, I would encourage you to talk to me, for one, and go vote on the Chromium and Mozilla bugs that we have open for these. Because certainly a lot of people think this is super rare, think it's not critically important. I actually think it's a great way to get musical control into the platform. And in fact, I'm going to end up with how many of you went to the local HTML5 user group last year where Peter Lubbers showed a DJ app? Okay, awesome. Only like 2 or 3. So nobody's seen even that before. So I wrote that originally because I was having this conversation over lunch at Google I/O last year with a DJ. And he asked me this question of, well, can you set playback rate to make things go backwards? And some other interesting questions that I didn't really have an answer to. And so I started playing with it, and I actually went straight from I/O on vacation with my family, and I spent about a quarter of my vacation actually sitting with my laptop in a chair playing with this and came up with this app. So this app basically is kind of a very simplistic version of a virtual DJ deck. And I'm actually controlling it with a real DJ deck. Like I bought this from, I forget where, B&H or something like that. And these are all over the place. Like most DJs these days actually use this kind of deck rather than a real turntable. And these are just MIDI controllers. Like when you spin this, it actually is sending MIDI messages to the computer. So I wrote the code to pick that up and wrote the code to do all the cross-fading between things. If you look at the top, it's kind of hard to see in this lighting, unfortunately. But if you look at the screen, it actually shows you the waveforms on here. So you can see them animate as it goes through. I can do things like set cue points, make it stutter, that sort of thing. I can even, if I want to, whoops. Oh, go away. Oh, that's, hang on. Needs to not be full screen to drop another. I can drop another sound file on here. I can even sit here and make one of them stutter. Or try to line them up, of course. Change the playback rate. In fact, the original point of this whole thing was to test, and you can, in fact, get them to go backwards. Not something that most DJ DAC apps actually do, but anyhow. There are a bunch of other features built into this. Thanks. Now, the other thing is, by the way, these things are still are working even though I don't have them on the screen right now. So my keyboard actually is still live right now. And I can still be playing things. If you look at my tabs up here, I have Web Audio Synthesizers, the third tab over. And in fact, my drum machine's still there too, with all of my sounds. It has a scheduling issue right now because of that set timeout problem I was talking about. So I don't want to start it playing because it would sound really awful. But I can combine all of those things together, even though I haven't directly combined the applications, and it will still end up sounding pretty good. All right. So I want to briefly give a status update of Web Audio. Web Audio is in Safari and Chrome already. Obviously, it's changing over time a little bit. We're still working on the specification. I guess that means it will soon be in Opera as well. Firefox is actually very hard at work. Mozilla's hard at work getting it into Firefox. If you look at the nightly builds, you have to enable it, but there is some very basic stuff already working, and they're super active on the working group right now, which is awesome. And almost more exciting to me is the story on mobile, where with iOS 6.0, we have web audio support on iOS now, so you can actually do a bunch of this stuff on an iPad or an iPhone, and there are some caveats. Processing power is not always great for things like convolution nodes and that sort of thing. And we're actually working very hard at getting it onto Android as well. I just got a new build from the developer yesterday, but I haven't had time to look at it. But the last build actually was looking pretty good. So opportunities here really are around gaming, obviously. Gaming's kind of a given with audio. But think about how you could use audio as feedback in your application UX. If you're a music person at all, I really encourage you to take a look at what you can do with music in the Web Audio API. And with that, I'll take any questions. Thanks.